All right, good evening, folks. Gonna walk through quickly the rest of the slides from where we left off last time. Gonna try and stay ahead of the game a little bit with things. My mic croaked the other day, so apologize for the sound quality in this. It should work out all right. It's just not production quality, but we'll make it do. So, again, just want to run through some specifics on some screening, and then what we'll do when we'll meet for our first Zoom lecture is we'll just jump right into the actual analyses or the screening within SPSS. So just as a recap, real quickly to run through basic assumptions of our regression. Up here, we have what we're going to work with is our 6 different assumptions of regression that we had talked about last time. But as we're going through and we're working on these, again, our primary concerns are when we violate assumptions, what are the impact on the regression coefficients and what are the impact on the standard errors? Again, these models are predicated in our inferences are predicated on the data meeting a certain number of requirements, and if we violate those requirements, if we're playing by a different set of rules, what does that happen to our estimates of the population coefficients in terms of our individual regression coefficients, and then what happens to our standard errors, right? Standard errors essential for inference tests, our significance tests, what happens to our hypotheses testing when that goes out the window, okay? So again, we've gone through these, so I'm just going to, just to bring us back up to speed, remember that our first assumption has a couple of different components to it. The first is that our predictors are fixed non-random variables. Remember that our fixed effects model assumes that what we've got is not a random selection of variables like we always do. Our fixed effects model assumes that we've gone through and systematically sampled all possible relevant values of the predictor that are out in the universe. And so our fixed effects model makes no assumptions regarding the distribution of our predictors. Our predictor distribution can look like anything at all with our fixed effects assumption. Again, let's say that our one of our predictor variables was color. What I've gone through and selected, say we've got 6 different colors in here, 20 of each one of those colors systematically, right? Same thing if I'm looking at, say, a predictor of extroversion. And a fixed effects model assumes that I've gone through and individually sampled all possible relevant scores on extroversion and have a sample of those within my model. Now, that's not how we run our regression models hardly ever. Very, very rarely ever. We tend to have a random selection of our values. And so what we end up having is we always violate, nearly always violate this fixed effects assumption, but that violation is negligible so long as my variables are multivariate normal. And so remember, this is why we need to go through in our screening and check the univariate distributions, univariate outliers, all of these bivariate assumptions, all this type of stuff, or bivariate plots, because we know we're going to violate this fixed effects assumption. Okay. We also have in this first assumption, we're assuming that our predictor variables are measured without error. Okay. This is also something that we always violate in practice. Measurement error in Y doesn't bias our parameters, inflates our standard errors, but we do get violations of parameters when we have measurement error in our predictor variables. Again, we're psychologists, we're in the field of psychological science, so we always measure things with error. Impact on the actual coefficients with measurement error is going to be complicated. It can go a lot of different ways. The main take-home message here is that we always want to use good measures. We want to use reliable measures so as to minimize the amount of bias that we have in our models. Okay, so this is our first assumption. Second assumption has to do with the distribution of our errors. Remember, when we're talking about our errors, these are residuals. These are calculated literally as the deviation of my observed y value for every individual subtracted from the expected value based on my model. And what we hope with these residuals is that they're have some normal distribution. Okay, so for every single predicted value of y across the entire set, we hope that everybody who had that same predicted value of y, their errors or their residuals are distributed evenly above and below that line. Okay, so we're going to have some cases with an observed score that's higher than predicted. We're going to have some cases that are going to be lower, have an observed score that are lower than what it was predicted, but hopefully across the range of that model, we have normal distribution of our errors. Oops. As we're working across this. Okay, so again, what we're concerned with when we have non-normal distribution of errors, if we have skewed residuals, our concern is that it can sometimes depress our standard error. If our standard error is depressed, that means our standard error is too small. If our standard error is smaller than it should be, that ends up biasing my test statistic, makes my tests too liberal. And so that's not good. I mean, it's nice for identifying things as interpretable based on convention, but not so great for actual science. We also assume that our errors or our residuals have constant variance across all range, or across the full range of X, or the whole range of our predicted values. Again, we're hoping that our residuals are normally distributed and that the distribution is homoscedastic. That means, again, for every predicted value of y, we hope that the errors around that predicted value of y are going to be the same impact, or the same regardless of what the predicted value is. What we sometimes see are bands going up and down. That's going to start to influence our standard errors again. Depending on the pattern, if I get an increasing fan shape, that depresses my standard errors, decreasing it inflates my standard errors, and that's going to impact my test statistics. So in terms of my residuals, normal distribution and constant distribution constant distribution of residuals throughout the model. Okay. Fourth violation, we assume that our residuals, that our errors are independent of one another. What we end up with is autocorrelation here. Luckily for us, we have a couple of different types of designs that lead to correlated errors. If we are running longitudinal data where we're observing the same set of individuals over time, we expect the errors at time 1 to be related to the errors at time 2, related to errors at time 3. If we're collecting nested data where we have children nested in classrooms, nested, say, in schools, we expect children from the same classroom, their errors to be more similar than any given child from classroom A versus any given child from classroom B, called it spatial autocorrelation. The nice thing is, excuse me, not the nice thing, we see our regression coefficients are unaffected. Our variance estimates are going to be biased. It's going to go through and underestimate our standard errors with these kind of data sets if we're not taking them into account. But luckily, we know that there are certain types of designs where this is an issue, and so then we can go through and assign the appropriate method for that. We also assume that our errors are uncorrelated with observed values of X. This is not something that we can test within our model by definition, but what we're hoping is that if we have a properly specified regression model, that is, all of the predictors that need to be in there are in there, all predictors that don't need to be in there are not in there, and then we've got the correct form of the relationship, then we are assuming that we have a correctly specified model. This is a theoretical concern, not something that we can directly test within the context of OLS regression, but something that we need to be thinking about. Okay, and then assuming zero population error. Again, OLS regression will guarantee an average residual value of 0, but it doesn't mean that it's necessarily going to be that way in the population. Again, this is something that kind of goes on in the background, but generally for our purposes, not something that ends up being a huge issue. And so as long as we have good measures and valid, reliable measurements, we're hoping that the impact of this is going to be fairly minimal. Okay, so this goes through our assumptions that we talked about at the end of class last time. Again, we've got these first 4 that we can go through and actually test. In terms of our violation of our fixed non-random variables, we're going to assume that we're going to have unbiased estimates so long as our predictor variables are multivariate normal. Here, we're assuming that each variable, all linear combination of variables, normally distributed and homoscedastic, residuals are normally distributed and independent. If those things all happen, we don't have to worry about problems with biases due to the violation of fixed effects. A lot of this has to do with looking at bivariate plots and univariate distributions, some of the stuff that we've done before, but in the example we'll go through and refresh your memory on some of that stuff. We're going to look at our errors to make sure that our errors, our residuals within our model are normally distributed and that they are homoscedastic. What we'll do is we'll look at a number of different plots to make a determination there. And then, again, independent errors are going to be more of a concern if we have repeated measure longitudinal designs, hierarchical analyses. These are more complicated designs. We're not going to get into much at all this semester, but something to be aware of. Okay, so that should bring us up to speed. So what we're going to do is I'm going to go through when we're talking about some different screening procedures. I'm going to use a data set that I put together so we have actual real plots that you can look at. And so the question here is we're running a regression model looking at the unique association of psychological flexibility. This is just your ability to sort of be open to change, sort of things go good, things go bad, you're not getting too worked up about that. So we've got a psychological flexibility measure, reward responsiveness. This is how excited you get about rewards, if that's a motivator for you. Behavioral inhibition, this is a sensitivity to punishment and sort of general anxiety stuff, and then willingness to utilize social resources. So your willingness to reach out to social resources that are available. What we're going to do is look at these 4 variables as predictors of perceived social support. So we've got a big sample, 335 individuals here, and these are going to be our measures. So our measure of perceived support is our MSPSS, psychological flexibility, AAQ, reward sensitivity, the BAS reward scale, behavioral inhibition, BIS, and then we've got our NOS. This is support utilization. So this is just a general data set that we're going to go work through. You don't need to have access to these data, but this is just for a conceptual basis, again, regressing perceived support onto these 4 predictors. Okay. So our model with a sample of 335 will be our predicted value of social support. Here's our intercept. This is the expected value of, oops, that should be MSPSS, that's an error. Oh, it is MSPSS, oops, okay. But this is our expected value of social support when all of these predictors are equal to 0. This is our unique effect. This is a beta 1 or B1 captures our unique effect of AAQ on MSPSS. B2, BAS reward, unique effect of BAS reward on MSPSS. B3, unique relation of BIS on MSPSS. B4, unique effect of NOS on MSPSS. And then here, this error term, this is our residual. Okay. In the model, on average, our error term is equal to 0, but what we want to do is take a look at the distribution and different characteristics of that. So what we're going to do, is we're going to go through, before we get into residual stuff, and this is going to be a recap, we're going to look at accuracy of plausibility, make sure that all our data are reasonable, that we don't have any out-of-bound values, looking for missing values. We're looking to look at our univariate distributions. Again, we need to see some reasonable adherence to normality, given that we're violating our fixed effects, right? So we need to see normal distributions there. We're going to look at univariate outliers, and then what we're going to do is we're going to look at bivariate plots, scatter plots between our various predictors and our outcome to make sure that our relations are all linear, that we don't have hidden nonlinear relations going on, and that our associations are, whoops, that should be homoscedasticity, not heteroscedasticity. Linearity and homoscedasticity of bivariate plots. Okay, so this is where we're looking for, again, our assumptions of multivariate normality and any possible specification errors or something that might suggest that. All right, so once we do that, once we get through steps 1, 2, 3, 4, and 5, now we can jump into looking at our residual plots. Okay, here is a series of panels looking at the predicted value of y on the x-axis versus your residuals versus your errors. In this first panel, panel A, here we're seeing a set of residuals that are normal and independently identically distributed. This is what we're hoping to see. We see that most of our residuals are kind of stacked up here around that center line, right? And then as we go across all the whole range of predicted values, we're seeing that the variability of our residuals around that center line is pretty much even across the whole board. Again, most of our stuff centered right here at 0, and then things increase and gone out. This is what we're hoping to see. This suggests clear concurrence with our underlying assumptions. Okay, here, if we're looking at our predicted values of y, or expected values y versus our residuals, we're seeing a clear negative skew here. Okay, we've got non-normal distribution of errors. Most things are stacked up right here around this 0 line. This is where the bulk of things are. But when we miss, we don't miss high, we miss low, right? And so we've got a clear skew here. This would be a violation of the normality of our residuals, would indicate that we have a problem here. Okay. Oftentimes, if we see something like this, it's because we've got a violation of univariate normality in one of our predictors or our outcome, perhaps. Panel C, this is another thing we can sometimes see in our residual plots. Here we have a clear evidence of nonlinearity. Okay, we've got a clear quadratic thing going on here. This would suggest that there's something going on. There's some relation in these data that are non-normal that we need to take care of. So this would be a residual plot that would indicate some non-normality. And D here, this is looking at heteroscedastic errors. We see that at low ends of my predicted value, we have very little variability, but as my predicted value increases and increases and increases, we have much more variability at the high end. Okay. Again, our concern with heteroscedasticity is that we're going to end up with violations or bias in our standard errors. In this case, we've got an increasing variability as our predicted value of our outcome increases. In this case, we'd probably expect to see some attenuation of standard errors, which is going to make our test too liberal, and then we're going to run into problems. We're going to identify things as having more evidence for them than we probably should. Okay, so again, when we're looking at heteroscedasticity, general rule of thumb, identifying severe violations as a spread by 3 times greater at the widest versus the most narrow. Here at the low end, very little variability in our errors here, a lot of variability here, and so we'd identify this as a potentially severe violation of our homoscedasticity assumption. Okay. All right, so how do we go through and actually look at these residual plots? How do we get these from SPSS? Here, and we'll walk through this in our demonstration that we do during class, but this gives you sort of steps to run through and grab those, but this is what your residual plot is going to look like in SPSS. Here you have your standardized predicted values on your x-axis. Okay, so these are my predicted values of MSPSS, and again, it's standardized, so the mean is 0 here. And then on the y-axis, what we have here is a studentized residual. Doesn't really matter all that much for our purposes, but what we're hoping to see, remember, is a plot that looks something like this. Okay. Now, if we go down through and we take a look, we've got a reference line here at 0. All right, so that tells us where our midline is, and so what we want to see is pretty consistent variability above and below that midline across the range of predicted values. This curved line here, this is a Loess regressor that I've included in here. This kind of is a smooth fit function, looking at the we're using this to look at nonlinearities in your data. So if we had a very clear sort of curved function or something like this, this Loess can be useful because sometimes we get data that are stacked on top of one another. It's hard to see where density is lying. So our Loess suggests that this is a straight line, a flat line is a reasonable fit to these data. My concern here is I've got this kind of thing that's going down, and I've got a pretty clear kind of linear function here, kind of an edge. What ends up happening is in this sample, most of our people are scoring the very highest level of MSPSS, and so we've got kind of a cap. And so because we have some negative skew in this distribution, most people are reporting the modal value for the MSPSS in these data is the highest value available, so people are reporting lots of support. And so we get this kind of, because we've got some skew in our data, we have kind of an upper threshold that's creating this here. So as I'm looking, if I look at sort of this part of the distribution, I'm not too concerned about heteroscedasticity. Everything looks like it's lining up. Here we start to get into something like, boy, is that looking problematic. Again, if I look right here, variability here compared to here is much less, but this is also just a small handful of cases at the high end, so we don't want to make too much out of that situation. If you've only got a handful of cases, you might have not a whole lot of spread here. So we're seeing some funkiness in this graph. Linearity doesn't appear to be an issue, but it does look like we might have, I don't know, maybe some negative skew in our residuals down here. Again, we're getting a lot more below than above. Not for the full range, right? Up here's looking okay. So linearity doesn't look to be an issue. Maybe some heteroscedasticity, although the stuff that we're seeing is probably, again, a function of the distribution of MSPSS and some negative skew there. The fact that the majority of people in the sample are hitting that top value, creating this edge right here. So we might want to say, well, residuals are looking a little bit strange. Linearity is not an issue. Violation of homoscedasticity might be something to keep an eye on, as well as maybe some distribution normality of my residuals. Again, as indicated by, particularly down here, we're seeing much more. My errors tend to miss low as opposed to missing high here. Okay, so this is what your graph will look like in SPSS. Here's the same graph in Stata. Again, center line here is my midline. We're expecting things to hover around above and below that. Here, this curved line, this is my Loess. Again, indicating a little bit of curve here, but not anything too terribly upsetting. But again, in this plot, we can see that some lower levels, when we miss, they tend to miss low, and then we've got this edge running right here. So certainly not, I don't know that I'm too concerned quite yet, but there's certainly strange things going on, or sort of things going on in these data that are notable. So Here, what we've done is just a kind of a visual inspection of linearity, normality, and heteroscedasticity, right? Linearity doesn't look to be a big issue, but maybe normality and maybe potentially heteroscedasticity, okay? So for normality of our residuals, we're going to run a couple different plots here, okay? What we can do is we can start to, or we can go through and request both histograms of our residuals, and if we request a histogram of our residuals, what we're hoping is to see a nice normal distribution centered around 0 of our errors, okay? And you all are familiar with histograms, you sort of know what those should look like. But then another plot that we can go through and take a look at that is useful, something known as a probability plot. So our normal probability plots are a nice way, different than our histograms, to identify whether or not any distribution, any variable, we could run these a normal probability plot with any of our observed variables. What we want to see is we can plot them against a cumulative distribution or a set of quantiles, and if we have data that are falling or meeting criteria for or meeting normal distribution, what we'll see is those data will fall along a positive diagonal, okay? And if we see deviations from normality, that ends up looking like deviations off of that midline there, okay? So if we take a look up here, in the PP plot, that's the favorite of the class, lots of laughs last time, so you can chuckle at home with that. And the QQ plot, just slightly different versions of this. We're going to use a PP plot in our screening, but it's arguably interchangeable, right? But in terms of thinking about what these distributions or what these plots look like, if we look up here in panel A, we have a normal set of data. Right now we're going to assume that these are residuals just because that's what we're talking about. But if I have normal distribution of my residuals, this is what my histogram would look like. We get a nice centered distribution. And if I create a quantile plot, so this is a QQ plot here, what I should see is that my graph lines up right here on this diagonal. I got a perfect slope riding right along one. That is looking really, really nice in terms of actual observed data, okay? But let's say if we don't have a nice normal distribution of a variable. Let's say we have something that's kind of square distribution. This would be something with a negative kurtosis, right? So if we go through and we create a histogram, we get a plot that looks something like this. From 0 to 1, very square distribution. If I take a look at a quantile plot, a QQ plot, what I'm going to see is this S shape here, okay? We can see if we compare that to the normal plot, we're seeing clear deviations off of that diagonal that are suggesting to us that we have a problem with negative kurtosis and a kind of a flat, boxy, rectangular distribution. On the other hand, if we have something that is pretty symmetrical, but it's looking very thin and peaked, right? This would be something with positive kurtosis. We see a slightly different, right? Again, if we take a look at my QQ plot and I plot it along the diagonal here, I'm saying it's not falling along a diagonal. I get kind of a curve in the opposite end. It looks kind of like a sort of an exponential, kind of flat, and then exponential up again. This is going to be indicative of non-normality associated with what we would typically think about as positive kurtosis. And then if we have, let's say, a distribution that's skewed, right? Something like this. We have a clear skewed distribution of our observed variable in our histogram here. And again, a clear deviation from this straight normal line. We get an exponential function here indicating a violation of normality based on my QQ plot, okay? So these are some plots that we're going to run. We're going to run both a histogram of our distributions, and SPSS will give us a PP plot so that we can go through and also get a better visual sense of violations. Okay. So in SPSS, These are our histograms and our normal probability plot. Here is our histogram that we know and love. We're seeing that we have, in terms of these are standardized residuals, it's not looking too bad, but we have maybe some negative skew looking here. You know, it's certainly not perfectly normal, and so we want to say, oh, how much of a concern is this? If we go over and we look at our PP plot here, actually doesn't look too bad. We're seeing some deviation from a straight line, but overall, normality doesn't look like it's a huge concern necessarily here with our residuals. So if these were data we would go through, I probably wouldn't have too many concerns in terms of the normality or the distribution of my residuals. Same thing if I go through and I run this in Stata. Similar plot within Stata, instead of just this straight, smooth, normal function, what I've done is I've requested a kernel density plot, which kind of maps a smooth distribution based on the data available. And so again, we see a little bit of a negative skew here. Again, when I'm looking at my PP plot here, we're seeing some violations off of that straight line, but for the most part, things are looking reasonable. So based on these data, I would probably not be too concerned necessarily about the overall distribution of my residuals, okay? So those are using our residual plots to go through and again look for linearity, looking at the normality of the distribution of our errors, and then also whether or not our residuals are homoscedastic in terms of their distribution, okay? But another thing we can get from our regression diagnostics is we can start looking at other types of problematic cases within the set. And there's three different things that we're going to go through and take a look at when we request output from our modules for screening, okay? First thing we're going to look at is a discrepancy, okay? A discrepancy are going to be assessed through our residuals, okay? Discrepancies are going to be determined by the difference between our observed outcome and our expected outcome for each individual, okay? And again, what we're going to do is we're going to look at some standardized residuals to go through and make a determination for are there cases where we're way off in terms of our predicted value? Because if there are, what we wanted to go through is maybe take a closer look at those cases because our model isn't doing a good job of accounting for the actual observed value of my outcome there. And if I get a lot of these, what I might have is a model that doesn't fit or a subset of individuals for whom my model isn't going to generalize. So wanted to go through and take a look at my discrepancies or my residuals, and this is going to be not violations, but problems in terms of Y space. What did I observe? What did I predict? And do I have an inordinately large distance there relative to the rest of my sample? So those are going to be my discrepancies. Leverage. This is going to be problems based on combinations of my predictor and my explanatory variables. What I'm going to see when I have large leverage values is I'm going to have unusual combination of cases. My leverages, these are my multivariate outliers, right? Do I have a strange configuration of predictors that don't make a lot of sense given the model, okay? And so here what I'm going to see is problems in X space, problems among my predictors that I'm going to assess through the calculation of leverages, okay? Again, when you see leverage, you should be thinking multivariate outlier. Yeah. And the last index we're going to take a look at is an index or a couple different indexes of influence. Influence is going to tell us the extent to which the inclusion of a case, the exclusion of a case is going to impact the model or any individual coefficient, okay? If we have a stable model, right, and if we have generalizable results, I should be able to drop people, add people without it changing results or my coefficients or my solution too much. If I start removing somebody and it completely, or one or two cases, and it completely changes my results, that's bad news. That suggests I don't have a stable model, or suggests that those individuals are problematic in some way. And influence is going to give us a sense for the extent to which individual cases, whether they're inclusion or exclusion, is going to impact the model and to what extent. Okay? So if we take a look down here at these three panels, we've got three different combinations of discrepancy, leverage, influence, and in a bivariate case, how this might impact our model. So here in panel A, if this is our set, right? So we've got 1, 2, 3, 4 data points, and then 5 here, okay? If I run a regression line through all of these, through the full data set, this solid line is going to be my regression line. If I get rid of this dark point here, my regression line is now a perfect line through these 4 linear points. What we would see here is a case, this black dot is going to be consistent with a moderate discrepancy, but a low leverage and low level of influence. Okay, so remember, our discrepancies is a deviation between my expected value and my observed value. Okay, so here for this set, here's my expected for everybody, right, with the full set. Here's my expected value, here's my observed value, very, very small residual. Expected value, observed value, expected value, observed value, expected value, observed value, very small residuals in the model for these 4 points. But this, by contrast, here's my expected value, here's my observed value, big residual, or at least bigger than what it was here, right? And so what we would see is some moderate discrepancy, right? My discrepancy, my standardized residual here is going to be quite large, but in terms of influence, the extent to which this case impacts my overall solution, not too much, right? If I get rid of this, then I've got a perfect straight line through these 4 dots. But with this, even though it's a moderate discrepancy, what it does is it looks like it just shifts the intercept down. My expected value when x is 0 is right here. Without that case, expected value is here with the case in, but it doesn't change the overall slope of the line. It just pulls everything down a little bit, okay? So even though we have a moderate discrepancy, I have low leverage because this, in my x-axis, this kind of falls, this still falls within the bounds of my x-axis, right? So it's not a weird x value. So it's got low leverage, and it doesn't change the model in terms of my coefficient or the slope of my line, but what we're just saying is some moderate discrepancy here. Okay. Moving over to panel B, a little bit different situation, quite a bit different situation here. What we've got is we've got a large discrepancy, okay? Again, here, observed value, expected value, observed, expected, observed, expected, observed, expected, okay? So for these 4 points, not much of a problem there in terms of discrepancy, but here, well, depending on how we would go through and collect this, if we're looking at the discrepancy, this is going to show up as a low discrepancy for the whole solution. But if I remove this, then I've got a big discrepancy. Then I've got a big difference, and we'll talk about this, a certain type of residual that gives us a sense for the difference between my expected value, if that case were excluded, and the actual observed value for that case. So here we have a potentially large discrepancy, right? And we also have a large leverage. For most of my data set, outside of this case, my data, my x values run from here to here, okay? But here we've got a value that's way different in terms of my x values. So we're seeing a large leverage, and then also a high influence, okay? With this data point in the case, here's my regression line. If I get rid of that, boom, complete change in my regression line. So here we're going to say that this is a point that has large discrepancy, large leverage, and high influence. Okay. Finally, in C, here we've got low discrepancy. The difference between my residual, between my expected value and my predicted is, or excuse me, my observed value and my predicted is minimal. Doesn't matter whether or not this case is in or not. But I do have a large leverage value. Here in X space, This is where my predictors are. This guy is way out here, so we've got a huge leverage value, but low influence, right? So if this data point is in or this data point isn't, has really no difference, meaningful difference in terms of the estimation of my regression line. The problem with this case is this is going to substantially suppress my standard error. With this value hanging out there, this makes it a much stronger line than if we're just looking at these cases here. And so what it's going to do, my concern here, even though it doesn't have a very high influence, my concern is what this is going to do to my standard error. If I go through and set this case way out on the otherwise regression line, but set it up way out here, it makes that look much, much stronger. And so I'm concerned with an underestimation of my standard error. Versus in this case, we're not seeing too much of an impact. Again, low influence is not really changing the slope of my line at all. But again, what I'm going to be concerned with the discrepancy here is that it's going to overestimate my standard error in terms of overall model, because we're not doing a very good job of accounting for this. Okay, so we're going to run through discrepancies, leverages, influences, and look at each one of these, because these all give us a little bit different information about our model. All right, diagnostics, looking at our discrepancies, okay? What we're generally going to be looking at in terms of our discrepancy, again, remember this is strange cases in Y space, right? We're going to see large differences here. If I have a large discrepancy value, I'm going to see this manifest as a large standardized deviation between my observed value and my expected value. Okay, and when we go through and we take a look, there's a lot of different standardized residuals that can be calculated. What we're going to focus on primarily in terms of our standardized residuals, something called an externally studentized residual. In SPSS, these are called studentized deleted residuals. In Stata, these are studentized jackknifed residuals. So some different names here. But essentially what this is doing with our externally studentized residuals, this is going to be calculated as the difference between my observed value of Y for a given case and the expected value of Y for that case in a model where that case isn't, where that observation isn't in there. Okay, so if we go back to this middle panel here, if I just look at the residual for this data point for the whole set, the residual for this case is very small, right? And if I'm just looking at my raw residuals, I'm going to say, okay, well, this model does a pretty good job of accounting for this case. What it doesn't tell me, or it doesn't reveal, is that this case is actually, because it has a large discrepancy and a large leverage, that it's actually drugged that regression line down to meet it, right? So if we look at the difference between this case and the expected value of Y in a case in the analysis in the model with this data in it, it looks like nothing much is going on, right? But if I go through and I look at the deviation between my observed value here and my expected value in a solution that doesn't contain just this one case, then I'm seeing a very large discrepancy between the expected, this observed value and the expected value if this case wasn't in my model. Okay, and so this is kind of the key feature of our deleted studentized residuals. It gives us a test for, again, the difference between my model predicted value for a case with those characteristics versus what we actually observed for that case. Excuse me, expected value of Y for that case in the set without that individual in there versus what we actually observed there. Okay, so again, if the observed outcome for this case is consistent with expectations in the larger set, so if we ran the model without that person in and took a look at their expected value and then compared it with what they actually scored, if I've got a low discrepancy, then my absolute value of my T residual or my externally studentized T is going to be low. If, however, the observed outcome from the case largely deviates from expectation, again in a model that doesn't have that individual in there, then I'm going to get a large residual, and that's going to tell me that what I've got is someone whose expected value is quite different than what the model is predicting. Okay. So the nice thing about my t residual, or my externally studentized t, is it follows a standard t distribution, right? So this helps me determine the magnitude of the case. T resid follows a t distribution with these degrees of freedom equals number of people in the sample minus the number of predictors minus 2. And so what we can do, just like we end up doing with z-scores, particularly if I've got a reasonably large sample, t distribution approximates z at large samples, I can just kind of take a look at those values for my studentized residual and see if I've got something that's looking large. Okay, so even though we have some, and the nice thing about this, these residuals, is that it gives us some metric to go through and compare against. Again, large studentized residuals somewhere between 2 and 4. Again, roughly saying this is 2 standard deviations above and below the mean, 4 standard deviations above and below the mean, right? So we can use sort of our general knowledge of standardized scores to make a determination on whether or not these residuals are at least the magnitude of those, but we always want to plot all of our diagnostic indices. The problem with the rules of thumb is they're often over-identify problematic cases, and then what you get doing is you get crazy and start cutting things out when they don't need to be cut out. So we always want to plot the distributions of these indices to make a better evaluation than what we would just get running on a yes/no decision off of any sort of general rule of thumb. Okay. So for the model that we ran, my studentized deleted residual here, if I go through and I take a look at the descriptors, and again, what I've done is I've just asked SPSS to save studentized deleted residuals, and then I've gone through and I've just run the descriptives on those, and I see that I've got a minimum of something that's quite low, about a little over 4 1/3 standard deviations below the mean, a max value here of 2.8, so my high value isn't too bad, but I've got some residuals that are very much on the low end, right? Now, if I just am using rules of thumb, I might sort of start to say, oh, these are terribly problematic cases. But if I go through and I run a box plot and a histogram, I see that I do have some cases down here, right? Looks like case 291, 292, 364. Again, I would want to go through, look through the data, make sure that these are cases. But what we've got is kind of a continuous distribution, or a continuous collection of scores that kind of go down. Now here we've got a set of 4 cases that are kind of set away from the rest of the distribution, right? So these are cases I might want to note and maybe sort of keep an eye on. But again, we also have a reasonably large sample here, 335 people. In a sample of this size, we're going to get some people who are at the extremes, and so we definitely want to note these: 291, 292, 364, 345 maybe. Again, want to make sure, look at our data set to make sure that I've got those numbers right. And so these are cases that I might want to keep an eye on, but I might not worry too much about this right now, even though we've clearly got some cases where we're missing something, right? So again, if I go through and take a look at the data, 291 has a studentized deleted residual of negative 4.34, negative 3.72, negative 3.54. Right? This is this collection of these 3 right here. So want to keep an eye on those and save those to see if they start coming up in other spots. Okay. And again, what we're seeing here, again, because our residuals are our observed value subtracted from our predicted value, what we're seeing is negative values here, suggesting that for these 3 cases, my model has largely overestimated the actual social support that these 3 individuals are reporting. Okay, Stata, same thing. Up here, we've just requested the um, descriptive statistics, again, it's going to be the same thing as before because everything's going to be the same here. Again, here's my histogram, here's my box plot of these, and so nothing different between the two programs here. Okay, so those are our discrepancies, right? Those are problems with in Y space. What we also want to take a look at is our leverages. These are our multivariate outliers. These are problems where we've got weird or strange combinations of predictors. So these are things going on in X space. And we're going to go through and we're taking a look at these through the evaluation of leverage values. Okay, and in general, we would say that our leverage is a measure of the distance from an individual case to the centroid of predictors. Remember we did three-dimensional hand gestures in class. Centroid is the mean of all predictors in your set. Leverage is just a metric of the distance in multivariate space between this individual case and the mean of all sample predictors in the set. And if we start to get something that's a very, very large leverage value, it suggests that we've got a strange configuration of cases, or excuse me, a strange configuration of predictors that don't fit with the rest of the sample very well. Okay, so depending on the program that you're using, going to run a couple different types of leverages in Stata, and where we typically see leverages, sort of a classic calculation of leverages. Stata will calculate it this way. Leverages range from a value of 1 divided by the sample size to a value of 1 with a mean of the number of predictors plus 1 over n. Right, that's a mean value. SPSS creates something called centered leverages, and so the range is a little bit different. These are going to range from 0 to 1 minus 1 over n, right? So the min and the max there. And what generally is recommended is leverages that are exceeding about twice the average in terms of just our leverages. So if p plus 1 over n is my mean value, we're looking at leverages that are maybe 2 to 3 times the mean value as a minimum threshold for further exploration. Again, we want to use this very carefully and not as a hard cut and dry criterion. If you do that, you're going to over-identify cases and you're going to start pitching people out when you don't need to pitch people out. Okay, so these are benchmarks for leverages. For centered leverages in SPSS, again, this is going to just be our threshold is going to be a little bit different. 2 times the number of predictors divided by n, or 3 times the number of predictors divided by n, so a little bit different. So just make sure that you're using the correct benchmarks for if you're using Stata or SPSS here. Okay, so please note that these are not if you just tell me that a case exceeded a threshold and so that you're recommending that it be thrown out, you're going to lose points because we shouldn't be doing this. We want to use this as a sort of a general reference point for identifying the magnitude of these leverages. But what we need to do is go through and do a whole lot more to go through and see, one, how does this case shape up to the rest of those in the set? And then 2, how do we go through, and we always want to, if something pops up as a multivariate outlier due to a large leverage value, we always want to go through and determine why that case has got a weird, what about that case is strange. Okay. So in SPSS, again, when we want to run our model, we can ask that it save our centered leverages, and here we've got our centered leverages, our minimum, our maximum. Okay, we go through and we plot our leverages. Here's a distribution, and again, we don't expect this distribution to be normal, but what we want to do is we want to see kind of where things are going. Okay, now with a total of 9 cases are going to exceed, if we use 3 times the number of predictors divided by n, this is going to give us 0.036, and we're going to get 9 cases with centered leverages that exceed our benchmark here of 3 times P over N, or 0.036 in these data, right? So we just take 3 times, we've got 4 predictors, times 4, divided by 335, gives us 0.036, right? Oops. And that's just, we're using, this is our threshold for centered leverages. So 71, 205, 403, 265, 260, 258, 380, 207, 270. It's a lot there, right? But if we look at this distribution, we have 276 is problematic, right? That's kind of a strange case. Things odd are going on here. But these other ones, they're definitely high, right? But we've kind of got this continuous distribution. This is a case that's very clearly in need of additional investigation. These ones are kind of a judgment call, right? Because it all just kind of continues on out here. So yes, technically, all 9 of these cases exceed our threshold for further investigation. But what we wouldn't want to do is automatically identify these as multivariate outliers and just throw them out. We're going to end up losing too much data if we do that. Okay, so we know that all of these 9 cases, but particularly 276, are strange for some reason because of some combination of X values. And what we're going to do, okay, so we know that these have some strange combination of X values. Same thing in Stata. This is not going to give us centered leverages, just give us regular leverages. So our min and our max are going to be a little bit different. But if we look at our histogram and our box plot, we're still seeing 276 come up as a high leverage value. Or this is probably going to be a case we're going to identify as a multivariate outlier, right? But what we want to do is we want to determine why. What about that case is causing it to be a multivariate outlier, right? So what I can do in Stata, you can do this, and so you'd have to write down pen and paper. In Stata, what I can do is I can ask for extremes of some value. So what I've asked for is extremes for my leverages, and then I've also asked it to give me the subject number, MSPSS, AAQ, BAS reward, BIS total, NOS, and then just said give me the high ones. And so we see here case 276 associated with a leverage value of 0.059, right, which is exceeding our what we would expect. Here, our benchmark with our leverages and not our centered leverages is 3 times the average. So 3 times 4 plus 1 divided by n is going to give me a threshold of 0.045. So I've got 5 cases in this set that exceed 0.045. But again, it's really 276 that's probably catching my eye the most, right? But what I want to do is see what about that case is strange. If I pull up my descriptive statistics for my predictors, right? My AAQ total, my BIS-BAS reward, or my BIS-BAS reward, BIS total, and NOS, I see that case 276 has an AAQ total score of 16, right? And if I look at AAQ total, so AAQ total is a little low, but that's not maybe too terribly strange. My reward is 11, that's 17, so I've got a really low reward score, right? More than 2 standard deviations below the mean of my sample. So it looks like I've got low BAS reward. My BIS, that's way low. So my behavioral inhibition scale, mean is 21. I've got a score of 12 with a standard deviation of 3 here. So I'm several standard deviations below the mean in my BIS. And then for my willingness to utilize support, 45, so I'm above the mean there. And so basically what I've got is, for this case, I've got a strange combination that looks like some combination of high NOS score combined with low BAS reward and low BIS. Remember, the MSPSS is our outcome. Leverages are just dealing with our predictor variables. And so just by looking and comparing the scores for this case by what's going on in the sample, I can start to make a determination on, what's going to go, why this is being flagged as a strange score. So again, really low BIS, pretty low reward, and a high NOS. It's a weird combination that's not typical of what we're seeing in this set. Okay. Now, when we go through the actual SPSS example, I'll show you how to hijack regression models to give you a little bit more of a systematic test of this, but always, always, always important to go through and make a determination for why cases are registering as multivariate outliers. All right. Last thing we're going to talk about is influence. Remember that influence is based on a combination of discrepancy and leverage. Now, I can have a case with a high leverage. I can have a case with a high discrepancy. High leverages, high discrepancies both have the potential to have an undue effect on the model, but just being a multivariate outlier, having a large residual alone, not sufficient to impact coefficients necessarily. What we want with our influence measure is looking at a combination of these, right? And our influence is providing us information on how our model would change with the exclusion of a case. So if I have that case not in there, what does it do to the overall model? Okay. And so we got our primary measure of influence we're going to use this semester is a statistic called Cook's D. This is going to give us an assessment of the difference in our coefficients for our full set of models versus coefficients if we would have excluded that target case, right? So this is different from our externally studentized residual. This isn't just expected value of y. It's kind of an amalgamation of, if we were to exclude this case, how would we see our coefficients for our model change? And with Cook's D, if we get a value that exceeds 4 divided by the sample size minus the number of predictors minus 1, these are giving us identifying cases that may warrant further investigation, although it seems like functionally this ends up being a pretty low threshold, but it's what we can go through and take a look at. Other measure that we won't use quite as much, but just so that you're aware, is cove ratio. This is going to give us a measure of the degree to which observation impacts the confidence intervals for our outcomes. If we've got cove ratios greater than 1, we're going to improve the precision event estimation, which seems like it should be good, but it's not going to be good if we've got a situation like this, right? What we would see is maybe a very, very a large positive covariance ratio, cove ratio for this data point, because even though what this is going to do is it's going to make this solution look a lot stronger than it should be if that wasn't there. We're just based on these data points. But with this one here, it's going to strengthen that regression line, and that actually ends up being problematic. Okay, so this is something that would be captured by cove ratio. If we've got a cove ratio less than 1, we got lower precision of our estimate in terms of influence. Our confidence interval is wider. And if we've got cove ratio minus 1, greater than 3 times number of predictors plus 1 over n, again, may warrant additional investigation. So we're not going to worry too much about cove ratio, worry more about Cook's D with things. Okay, so remember, influence is a metric of the combination of leverage and discrepancy. So in SPSS, I can request to say if Cook's distance, cove ratio, here's my box plot of Cook's distance. And again, this is why plotting is going to be a much, much more effective way of identifying potentially problematic cases than using thresholds, because we're going to see a lot of scores here that are high, right? If I go through and I take a look, I'm actually going to get a total of 17 cases with a Cook's greater than 0.012. And again, this is just 4 divided by 335 minus 4 minus 1 gives me 0.012. We have 17 cases. I'm not going to throw 17 cases out of my set, right? But if I go through and I plot this, I can say 380, 292, and 276 are all cases that are potentially problematic for me, right? These are cases, 276 in particular, that have the potential to impact my coefficients by quite a great deal. Same thing, cove ratio, a little bit different. Again, this is looking at width of confidence intervals. Here we're seeing 345, 364, 292, 291 as generating high values. Again, 25 cases exceeding my threshold. This is why we don't just use rules of thumb to make decisions, because we're going to make poor decisions most of the time with that. Plotting it out, you can say, okay, yeah, these are high, but these are the ones that are problematic. Okay? Same thing in Stata. Here, we're just requesting the descriptive statistics for Cooks and covariance. Here, what I've done is I plotted covariance ratio as a histogram, just to give you a little bit different look at it, right? And again, we're seeing 1, 2, 3, 4 cases. Whoops. 1, 2, 3, 4 cases. So a little bit different way to look at it. Here, looking at Cooks, what I've requested in Stata is a drop line plot. And this is another cool way to go through and take a look at things. Again, here, 276, 292, 3. These are all cases that are way above sort of where everything else is, right? So using this as a way to go through and say, oh, maybe these are cases that I might want to take a look at. So just different ways of plotting it. Graphical representations are going to be your very best way of identifying cases that might need further investigation. All right. So what we've done throughout this point is we're going through looking at different cases and taking a look and marking down which cases are potentially problematic, okay? And then what you want to do is see if you have repeat offenders and want to go through and make a determination on sort of whether or not we might want to recommend continued evaluation of those cases, maybe run a model with and without those cases, look at the impact on our model. Again, our main concern is we don't want to have, particularly if we've got a reasonably sized sample, if we've got one case or two cases, a handful of cases that make or break our results where things completely change based on their inclusion or exclusion, that's bad news. We don't want to have those in the model, okay? Or at least we want to understand why they're causing the impact that they are. So those are the statistics that we're going to be most concerned with for our purposes. Now, there are other types of more advanced regression diagnostics. We can do a closer look at linearity. If I find that I have some violation of linearity, okay, I get a regression model or a residual plot that looks something like this, right? My concern is, particularly if I've got 3, 4, 5 predictors, I don't know exactly what predictors or what combination of predictors are causing that nonlinearity. If I wanted to, or I'm seeing something like that, what I can do is I can go through and look at a scatter plot of my residuals in the y-axis against my individual predictors, try and see if maybe I can find what variable or combination of variables are contributing to nonlinearity in my data. Okay. Additional influence statistics, DF beta, looks at the impact of an inclusion-exclusion of a case on my coefficient for my individual predictors. Again, what I'm looking at is here I'm going to get let's say I've got 3 predictors in my model. I'm going to get DF beta 1, DF beta 2, DF beta 3, and it's going to give me the influence not just on the set of coefficients as a whole, but on individual coefficients. We can look at these using an index plot, or we can go through and take a look at sort of the values. But what this would tell me that Cook's won't is for this individual predictor, how does my coefficient change if I have that case in versus I don't? So a little bit more detailed stuff. Independent error. Okay, are my errors independent of one another? Again, we're primarily going to be worried about this in terms of just very specific designs, but there are ways where I can run an index plot where I look at my residuals on my y-axis, and on my x-axis I just plot cases in order of data collection. If I see, let's see, I'm doing some sort of assessment or some sort of study, and I see that at the front end my residuals were very low, but as my study continues, my errors get larger and larger and larger and larger. with each successive participant that I ran, that could suggest something. Now, that's not a design issue, but it might suggest that I have a research assistant or an experimenter that's getting increasingly off base in terms of standardization or things along those lines. This is something we could look at with an index plot, seeing increases or decreases in error over time. Specification error. Do I have everything in my model that needs to be in there? We can run something called added variable plots, looking at the impact of hypothesized predictors in and out. Something we do, kind of cool. We won't worry about it here. And then the last thing that we will spend a little bit of time on is something we're going to call combination plots. What we're doing here is we're going to have plotting different indices of discrepancy, influence, leverage within the same plot. So trying to combine, instead of individually working through discrepancies and then leverages and then influence values, tying these all together. So Stata does a really nice job of allowing you to map on multiple plots within the same figure. What we have here is a leverage by squared residual plot. So here in the x-axis, we have our squared residuals or our squared errors. We square it so that they're all sort of pointing in the same direction and positive. So if I square a very, very large residual in the positive direction or square a residual that's very, very negative, they all show up on the same side, right? So it turns everything positive. And here we have our leverage value, right? So here have our multivariate outliers. Here we have our discrepancies, squared discrepancies. And what we're looking at is individual influential cases are going to be those with large leverages and large squared residuals. And you're going to put them right up here in this upper right quadrant, okay? And so if I find cases that are hanging out up here, those are going to be cases that I very much want to go through and take a look at, because what we've got there is we've got a large squared residual, a large discrepancy, a large leverage. Stuff up there would be problematic. Now here we've got a case that has a high squared leverage, 291. This guy popped up previously, but the leverages, so this is a case that is pretty typical in terms of the predictors. We were just way off on the prediction. The outcome was way different. So this is probably not anything we're worried about too much here, right? Same thing here. We've got a very, very strange combination in 276, strange combination of predictors, but my residual isn't too bad, right? It's still, I mean, it's not great, but it's sort of within, it's not too extreme, okay? Now, if I were to get rid of this cluster of cases and just look at that, then this is going to be up in the corner, but we're not, I don't know, maybe if we wanted to go through and then identify these 5 cases and pull them out, but then this is now going to be a big case. And so, again, it's that wanting to make a determination on sort of how far we're going to go and being careful about what we're identifying as problematic cases. So here, yeah, I mean, these are maybe cases I might think about looking in, but probably in sort of based on running these data, it doesn't look like it actually makes too much of a difference. But things we would flag and sort of say maybe we want to look at this a little bit further. Okay. Other combination plot we can run here, again in Stata, I really, really like this one. Again, this is the same thing. Here we have leverages on the x-axis this time, and our studentized residuals on our y-axis, right? So we've got a leverage by residual plot. But what we're doing here is we've also plotted in Cook's D, our measure of influence. And so here, the size of the circle is proportionate to the size of Cook's D. Remember, 276 had a very large Cook's D, so the circle around this is quite large. Again, what we're looking at in this combination plot is cases in the upper right corner, the bottom corner here. So 276 was up here when we have leverages on the y and normalized residuals on the x. Here we flip it around, and now we're seeing 276 does start to end up here at the top of the plot. So maybe 276 would definitely be a case. This is something with a high leverage. Residual is not huge, but it's my studentized residual versus my normalized residual squared. My studentized residual is still pretty high. And so this would be a case here that I might want to take a look at, or if anything were happening down here. Again, this would be, again, a large leverage and a large negative studentized residual. Remember, our studentized residuals with large samples, we can treat these functionally as z-scores. So 276 might be a case to take a look at. 380 has a larger Cook's D, but I don't know if we'd want to worry about that as much. 276 would be the one we'd look at here. Okay. So in the SPSS, we can kind of do the same thing, manufacture-ish, calculate our centered leverage value here by our studentized deleted residual. Up here we see a case up in the upper right corner. What I can do in SPSS, it can't do sort of quite some of the stuff here, but I can go through and I can label. So this is the same plot. I've just labeled the case, not the case number, the observation number, and added a label here. So this is observation 335. That just says that this is in my total set. This is the 335th observation. This is actually 276. The subject number is 276. It's just the very last, the way I've sorted it is the very last case in the set when I created this plot. So please note that when you do this in SPSS, these labels indicate the position of the case in the set, not the participant numbers. Okay, so you get yourself turned around there. So from this screening that we've done, it can often be helpful to go through and see try and identify what came up as the bad penny. What are the cases that come up again and again and again and again? Here we see the case 276 didn't flag that as having a real high studentized residual, but large leverage value, large cooks in my combination plot, that came up, right? So 276 would definitely be a case I would want to look into a little bit more. And then after that, we got 380 came up with a high leverage and a high influence. So I might want to take a look at that. 292 with a residual and a high cook, so maybe 292, but I'm less concerned. If I was going to go through and choose a couple of them to look at, I would probably go with definitely 276, and maybe 380 is a little bit more investigation there. Yeah. So, all right. So, other thing that we'll want to take a look at in terms of screening multicollinearity. Remember that the unique contribution of our predictor decreases as we start to get stronger and stronger correlations with other variables. And if we have really, really high collinearity, our regression coefficients become unreliable. We get really wild standard errors that will jump around. So we'll have standardized coefficients that indicate very, very, very strong associations with my outcome, but that are registering as not interpretable based on conventional benchmarks because my standard error is really big, right? So I've got a massive standardized coefficient. I've got maybe a beta value of 0.6, right? Which is really large, but then it's not, or associated with a p-value of 0.0 or 0.50 or something like that, right? Usually an association of that magnitude would for sure pop up, but it doesn't. This can be due to collinearity, and what we see is our regression coefficients are going to be stable. Minor alterations of the data include people, exclude people. All of a sudden, things start jumping around. Now, if we're just interested in the coefficients, my coefficients themselves are unbiased, but very difficult to interpret because it wreaks havoc on our standard errors. Okay, so rule of thumb for our bivariate correlations, because we're going to look at bivariate correlations, and then we're going to look at those collinearity diagnostics that we had talked about before. Rule of thumb of 0.9. If I've got variables in my data that correlate with one another 0.9, you've measured the same thing twice or three times or however many times things come up, right? But so anything that would even get close to that is something you'd start to be concerned about. VIF, variance inflation factors, of around 0.2 have started to become identified as potentially problematic. If I take a VIF, a variance inflation factor of 2, again, my rule of thumb is that my VIFs need to be less than 10. But even if a VIF is at 2, right, a VIF of 2 indicates about a 40% increase in corresponding standard error for that coefficient, or excuse me, for coefficients relative to predictors that were uncorrelated. And I can get that 40% if I take the square root of my VIF. So if I take a square root of 2, I get 1.41. It's about a 40% increase in my corresponding standard errors. So again, if we get anything that starts to look high, we want to take another look at that, particularly look at my standard errors to make sure that collinearity hasn't wreaked havoc on my tests. So in SPSS, here I've gone through and I've requested my output. If I just request collinearity diagnostics in my screener, what I'll get is this here. And again, I'm going to want to see a tolerance level of less than, if I have evidence of collinearity, tolerance levels that are less than 0.1 are problematic. Again, asterisk, if you get anything close to that, you're way out of bounds. But here, tolerance levels all look reasonable, so we're good there. Variance inflation factor, just sort of a linear function of my tolerance. Again, values greater than or equal to 10. Again, if you're anywhere in the vicinity of that, that's problematic, but here we're looking okay. And then if you do find something across multiple sets, because what we can get is combinations of variables that are causing collinearity. Our collinearity diagnostics here, these can be helpful in determining which combination of variables are becoming problematic. So if I have a combination of eigenvalues that are close to 0, combined with condition indexes greater than or equal to 30, combined with variance proportions greater than 0.5 on 2 or more variables. So now as you get sort of slower and lower and lower, these get down. But if we were to see problems up here with collinearity diagnostics, well, we would look down here and look at, now if we weren't being careful, we would say, oh, well, this has an eigenvalue very close to 0, combined with a condition index exceeding 30, with variance proportions for Bass reward and NOS total is very highly greater than 0.5. We might say, oh, we've got a problem with correlation between Bass reward and NOS. But again, if we look at our tolerance, our VIF, we see we're fine there, so we don't have to worry too much about that. But so this is primarily what you're going to look at. But if you see that you have potential problem with multicollinearity, you can go down through and take a look at your variance proportions to help you tease out where that's actually going on. Okay, same thing in SATA. After I run my model, I type VIF, gives me my VIF and my tolerance here. Again, it's the same thing we got there. And then if I use coldiag2, this is a command you have to request, but after I run my regression model VIF, get this, coldiag2 will give me my variance proportions and things that we got previously. Okay. So, summary of our procedure. First, going to look at accuracy, plausibility, like we always do. Look at missing values, like we always do. Univariate distributions, like we always do. Univariate outliers, like we always do. Then we're going to start to look at my bivariate relations. I'm going to get scatter plots for a combination of all my variables. What I'm looking at is we want to make sure that we don't have any nonlinearity in those scatter plots, and we're looking for sort of error distributions, looking at homoscedasticity in the combination, the associations of my observed variables. Now, technically, I'm more concerned with homogeneity, violations of homoscedasticity within my residuals, but checking my bivariate plots is still something that's important to go through and take a check on. Also looking for specification error if I've got nonlinearities or strange things can suggest that there's maybe a variable that's missing from my model that needs to be in there. Then I'm going to look at my residuals. I'm going to look at my error distributions. I want to make sure that they're normal and homoscedastic. And I'm also going to look at nonlinearity that might indicate some evidence of a model misspecification. Then we look at discrepancies, problems in my Y space, leverages, problems in my X space, influence the combination of these. Again, what we're concerned about is potential for undue influence of a case, collection of cases, and last, going to finish up with making sure that we don't have collinearity across our stuff. Okay, so that does it. That's a lot. There's a lot going on. We're going to give you lots of opportunities to run through these. And again, once you get a file set up, a system put together, it starts to become sort of much easier to run through this stuff. So that does it. Again, this will save us some time. So go through, watch this, and if you have any questions, please write these down, and we can bring them up during as we're walking through the actual example in class. This can be a lot to wrap your head around. Again, we'll do a walkthrough, spend our time doing that, but that will help get us all set up and ready to go for this next problem set. Okay, hope you guys are well, and looking forward to seeing you on Wednesday.